chapter 17, and we're going to look at the acid-base properties of ions and salts. So what's really important here in determining whether a salt is even going to act like an acid or a base is determining whether or not it will ionize water. So not all ions will create an acidic or a basic solution. Only those that ionize water will. All other ions will remain neutral. So what we see here we have HBr, hydrobromic acid, that will ionize the water. Then we also have sodium bicarbonate with water. Now the bicarbonate part will ionize the water, but the sodium will not. It is something that is just going to remain neutral and will not change the pH of the water one way or the other. So we're going to be looking at the acid-base properties of salts and the ions they contain. So we're going to start off looking at anions as weak bases. So in order to make sense of this, you're going to need to do two things during this entire lesson today. First of all, you need to think of that anion as the conjugate base of an acid. And that's going to be the first part of our lesson, is focusing on these anions. The second part of the lesson, we're going to be looking at the cation and thinking of it as the conjugate acid of a base. Once you get the anions as weak bases, doing the cations will not be very difficult at all. It follows very similar patterns and rules. So let's go back and make sure that you can pick the conjugate base of an acid. So what I want you to do is to circle the conjugate base for each one of these reactions. So our first reaction, we have HCl plus H2O. And take a moment and go ahead and circle which one you think is the conjugate base. So let's start off. Make sure I can get this to work right. Let's start off first of all. So HCl, hydrochloric, hopefully we know that is definitely an acid. So in this case, the water is acting like a base. And it's going to be the chlorine ion that is going to be the conjugate base, and the hydronium ion that's going to be the conjugate acid. All right, our next one. Once again, what is our acid? What is our base on that left side of the arrow? So H2SO4, hopefully ladies, you are memorizing your strong acids and your strong bases. And because once you have those memorized, everything else is going to be considered to be a weak acid or a weak base if it is an acid or base. So H2SO4, this is sulfuric acid. It is a strong acid. And water, once again, is acting as our base. And once again, we have here our conjugate base, and then the hydronium as our conjugate acid. And our last but not least, we have hydrofluoric, and once again, acid, and with water acting as our base. So here the hydronium, once again, is the conjugate acid, and the fluorine ion is our conjugate base for that reaction. So notice for these same reactions that we had on the previous slide, our first two reactions do not have that double-sided arrow. Only the third reaction does. Why do you think that is? Well, namely, that has to do with the fact that the hydrochloric and the sulfuric are both strong acids. So these are going to go to completion, whereas the hydrofluoric on the other hand, this is considered to be a weak acid. So we are not going to get full dissociation of that acid in water. So that's why we have our double arrow for that particular reaction. So we can take this a little bit further to see it in more detail. So if we have that fluorine ion and it is still in there with water, so you got to think of it as all of this here is all happening in the water at the same time. Now, fluorine as just an ion, you'll have to remember fluorine is the most electronegative element on the periodic table. It does not want to be by itself. So it has no problems taking a hydrogen, taking a proton from water in order to go back and form that hydrofluoric acid. This is why it's a weak acid, and why it doesn't want to disassociate the way that the sulfuric and the hydrochloric. The fluorine atom or ion is just too electronegative to ever just be by itself for very long. So here is a couple of rules that you need to memorize right here. The anion that is the conjugate base of a strong acid is pH neutral. So in other words, this chlorine here, this HSO4 over here, both of these would be neutral in the solution. But the anion that is the conjugate base of a weak acid is itself a weak base. So what we have here with this fluorine, when it is by itself, this is actually a weak base. All right, so once again, we have a couple of rules here that you need to memorize, and we're going to see when we cover the cations that we have a very similar thing going on with this. But these two rules do really kind of form a cornerstone of this lesson, and we're going to keep going back and using these rules over and over again in this screencast. All right, so here's a table that kind of shows you what I'm talking about. So here we see our acids, and then we see their conjugate bases on the right-hand side. And the stronger the acid, the base, it's negligible. We say it's just neutral. We see that the only way that our conjugate bases are actually do act as a base is when it comes from a weak acid. And then once again, we see that if we have a strong base, that their conjugate acid is so weak that we really say that it is negligible or pH neutral. All right, so let's work on this a little bit more. And so what I have here is a chart that has some acids for some of the questions, and it has bases for other questions. And I want you to practice deciding what the strength of the acid is, and therefore the anion base. All right, so our first one is HCN, hydrocyanic acid. So the very first question you need to ask yourself is this part of the 6 strong acids that I had to memorize? If the answer is no, then we are going to go ahead and say that it is a weak acid. The anion from this acid would be that cyanide. And if hydrocyanic is a weak acid, then the conjugate base strength is also going to be weak. Now, you please feel free if you want to pause the video and try this on your own and then press play again and see if you got the right answers. Go for it. If you're still not feeling really certain about this, keep following along with me, but at some point, and maybe for the last two, think about stopping the video and trying it on your own. All right, so here is our anion. So our acid is going to require us to just add a hydrogen. So we're going to make that H3PO4. Okay, that's phosphoric acid. Once again, the question to ask yourself is this one of my 6 strong acids that I am supposed to memorize? Answer, of course, is no. So we're going to say that it is a weak acid, and therefore this conjugate base here is also going to be weak. All right, so then the next one, HBr, hydrobromic acid. Now, this acid is certainly one of the strong acids that you are supposed to memorize. So we're going to say that's a strong acid. The anion would be that bromide ion. And this one is going to be neutral. Remember, if we have a strong acid, its anion, its conjugate base, the strength is going to be neutral. All right, and last but not least, now we're given an anion and we got to see what acid did that anion come from. All right, so we're going to add that hydrogen, that proton there. And because this is not part of our 6 strong acids, we're going to go ahead and say this is weak. And therefore, as a conjugate base strength, it is also a weak base. All right. So this is a good point also to stop the video and go ahead and work on that end of chapter 17 problem number 95, which is very similar to what we just did. All right, so now let's look at those cations as weak acids. Very similar idea here as what was going on with the anions, but of course, since it's chemistry, we got to add just a little bit more to it. So these strong bases, once again, they will completely disassociate, just like our strong acids completely dissociate. And their cations, we have a new vocab word here, ladies, counterions. So that cation that comes from a strong base is called a counterion. And once again, though, because of it was a strong base, because it's completely disassociated, we're going to say its pH is neutral. Now, the conjugate acid of a weak base will be a weak acid. And then we also have this new special little twist on determining if we have a weak acid or not. And that is if we have a small, highly charged metal cation. And these are going to be our cations that we see with this +3 charge. Those, anytime you have that cation that was part of that base, then we know that these cations will form weak acids. All right, so let's try it again. This time, though, having bases and determining what our cations would be from it, or taking these cations and determining what our base would be, and therefore being able to determine base strength and then the conjugate acid strength as well. Once again, you have to have those 6 strong bases memorized in order for you to feel effective at being able to do this kind of work, this kind of question. All right, so here we have strontium hydroxide, and its cation is just going to be that strontium. Okay, so strontium hydroxide, because we have a metal that's a group 1 or a group 2 metal, and I think strontium is a group 2 metal. Sorry guys, I'm trying to pull out my periodic table to look. Yeah, so strontium is a group 2 metal, and anytime we see a group 1 metal or some of the heavier group 2 metals with hydroxide, automatically it is a strong base. Okay, so that is definitely a strong base, and therefore our conjugate acid is going to be neutral. All right, so now we have this manganese. Now, oh, look what we have here. We see that 3+. So we have this metal ion that's very small, highly charged. So automatically, as soon as we see that, we don't even have to worry about this base or base strength, because automatically that's going to fall under the category of the conjugate acid being weak. All right, our next one, the base for this one, oh wait, sorry, started at the wrong place with that. And it's not going to let me erase. Nope. Okay. So let me just try to write around that. So we're going to have, let's see, C5, H5, NH2. Okay, so this one's kind of a strange base. So whenever we see these NH combinations, instead of it being where our base comes from this hydroxide, here our bases are going to be where we see this addition of a hydrogen with that nitrogen. So once again, is this considered one of those strong bases that you had to memorize? No, it's not. So this is a weak base. Therefore, the conjugate acid strength is also going to be weak. All right, and last but not least, lithium hydroxide. And yes, this is a strong base because we have lithium, which is a group 1 metal. And so therefore, our conjugate acid is neutral. Once again, this is a great time to stop the video and go ahead and work into chapter problem number 99. All right, so the entire point of what we've just been doing with determining that conjugate base or that conjugate acid strength is so that we can look at a salt and determine if that salt is going to create an acidic or basic or even just a neutral solution. So let's look at how this can be done. All right, so here we are, we're given a salt. This is strontium chloride. And what you're going to want to do for these is you're going to want to break apart that salt into its ions. So here we're going to have strontium, and then we have chlorine or chloride ion. And the question you're going to ask yourself is, what is that, okay, because this is the cation, what is the base that that the strontium ion came from? And so this is going to be strontium hydroxide. And then we're going to ask the same question. What acid can be made from this chloride ion? And that would be hydrochloric. Now the question becomes, are these two, this base, this acid, are they strong or are they weak? Well, this is a strong base. And hydrochloric is also a strong acid. Now remember, what did we say? If we comes from a strong base, then the strontium itself is going to be neutral. Once again, our hydrochloric, strong acid. So this one, the chloride ion, also has the potential of being neutral. So this particular salt, the strontium chloride, is just going to form neutral solutions. All right, let's look at another one. And here we have aluminum bromide. So once again, let's break it apart into its ions. So aluminum and then the bromide. And look, here we have once again that small highly charged metal. So we already know that this is going to form a weak acid. And then the bromide, this is going to be able to form hydrobromic, which is a strong acid. Therefore, if it's going to be able to form, the bromide ion is going to be neutral. So we have a weak acid with neutral. So that means this aluminum bromide can form an acidic solution. All right, so I know this is a little confusing, and I do have a few more examples for us to do. Okay, so for this one, once again, we're going to do the same thing. Let's break it up. There's that sodium ion, and then we're going to do the formate ion. And so this would be forming, this sodium ion would come from the strong base. So sodium hydroxide is a very strong base. Once again, if it's a strong base, then that ion is going to be neutral. Then the formate ion is going to be able to form formic acid. So that is CH3O2. And this, once again, is it part of your list of strong acids? If the answer is no, and this one certainly is not a strong acid, it is a weak acid. Therefore, this can form a weak base. So therefore, we're going to say that this salt will form basic solutions. All right, so here is another one. Let's break it apart. So we have CH3, NH3, and then we're going to have NO3. Let me put my signs there. Now, do I expect you to necessarily know that this polyatomic, CH3, NH3+? Absolutely not. But what I am hoping is that you know NO3, nitrate, and so if this, you already know this polyatomic, then the rest of what is in this salt must be part of the cation. So some of what I am looking for you to do is to work backwards from your knowledge. You certainly don't have knowledge about CH3, NH3, but you do have that knowledge about the nitrate. And therefore, if nitrate, we know, is a anion, the rest of it must be forming the cation. All right, so this would form a base. Okay, and this is considered a weak base. Usually when you see this NH combination, NH3, ammonia, that's a weak base. We're going to be forming weak bases. You don't need to worry about this NH combination being anything other than a weak base. And then we have HNO3, which is going to be our nitric acid. This is a very strong acid. Therefore, this is going to be neutral. This is a weak base, so this is going to form a acid. Therefore, the entire salt is going to make an acidic solution. And I think I have one more example. Yes, I sure do. Okay, so this one is very interesting. So let's break this one up. There's that ammonium, and there is the fluoride ion. So NH4, that base that it comes from, there's that ammonia, which I've already just told you is a weak base. And then the fluorine, the acid it comes from, is hydrofluoric, which once again, that is a weak acid. So weak acids can form bases, weak bases can form acids. So my oh my, what do we do about this one? Because we see that it can be an acid or a base. When you have this situation, this is when you need to look at the K values, the Ka and Kb values for these in order to determine what they're going to be. Don't forget you have Ka and Kb value charts in your in chapter 17, and that's what you're going to use to get your values. But all of this is going to be based on that formula, which was that Ka times Kb equals Kw. And this is a good time to check your memory. And remember, please remember that Kw, this you don't have to look up, because Kw is always going to equal 1 times 10 to the negative 14th. So we are going to manipulate this equation once to solve for Kb and the other time to solve for Ka. So we are going to start off with finding the Kb for that fluorine ion. So the manipulated equation, and our values that first of all know, and then also for the Ka looked it up in the textbook, we want to have 1 times 10 to the negative 14th over 6.8 times 10 to the negative 4. And once you put that in your calculator, do a little punch and crunch, you're going to come up with 1.471 times 10 to the negative 11th. Now let's go and do it all over again, this time solving for the Ka of the ammonium ion. So once again, Kw, this time over Kb, and 1 times 10 to the negative 14th over 1.76 times 10 to the negative 5th, punch and crunch, and you're going to come up with 1.562 times 10 to the negative 10. So now what you're going to do is you're going to look and see which one of these values is larger, and that's going to determine whether or not that salt is going to form an acidic or basic solution. So we see that this value is larger, so that the ammonium ion is a stronger acid than the fluoride ion is as a base. So therefore we're going to say that this salt is going to form, possibly, there we go, acidic solutions. Okay, so let's go over that one more time. When you get in a situation where you have two ions, one that comes from a weak base, the other that comes from a weak acid, you are going to have to use this Kw formula and go use your tables and to find your Ka value for that ammonium, and then find the Kb value for the fluoride and put that into that formula that's been manipulated to solve for either the Kb or the Ka. Do a little punch and crunch, see what numbers, what K value is larger, and that will determine whether or not your salts will be acidic or basic. In this one, our Ka was larger, therefore this is going to form acidic solutions. All right, so that is a whole lot going on. I have a table here in your notes that you can use to determine whether or not your salt is going to be acidic, or if it's going to be basic, or if it's going to be neutral. Okay, you have a chart very similar to this in your textbook. So if the anion is strong and the cation is strong, then it's going to be a neutral salt. That salt will form neutral solutions. If your cation is the conjugate acid of a weak base, then we're going to have an acidic solution when the anion comes from a strong acid. All right, so this is pretty easy to follow. You are welcome to memorize it, but honestly, if you have your 6 strong acids and your 6 strong bases memorized, and you can determine whether or not that conjugate base comes from a strong acid, or that cation comes from a strong base, the rest of this is going to fall into place with those rules. Strong acids are going to form a neutral base. Strong bases will form a neutral cation, conjugate acid, okay? And then it's only really our weak bases and our weak acids that are going to allow those conjugate bases and conjugate acids of weak acids and weak bases that's going to allow us to have a salt that can either be acidic or basic. All right. So once again, this was a great time. You can stop the video, work into chapter problem number 101. All right, really fast. Polyprotic acids. Right here, I'm just looking to introduce you to this word, what it means, your ability to recognize a polyprotic acid. And so these are acids that contain 2 or more ionizable protons, so H2SO3. Because of that 2, right there, next to the hydrogen, that's how we know that it's polyprotic. And then I'm sure you can think of some other ones. H3PO4. This particular acid has 3 ionizable protons. And that's it. That's all we're going to do with polyprotic acids. Do you understand what the word means? Can you look at an acid and determine if it's polyprotic or not? That's it, ladies. All right, so now we're into section 10 of chapter 17, where we're going to look at acid strength and molecular structure. So why do some compounds containing hydrogen, containing that act as an acid, and others do not? And why do we have some strong acids and others are weak? So we're going to look at that and try to answer that question in these next few slides. All right, so once again, we have some more vocabulary that you're being introduced to. We have 2 categories of acids. We have binary acids and oxyacids. So what we're going to do is we're going to start off by talking about these binary acids. These are acids containing hydrogen and only one other element. So this Y here would represent any element on the periodic table. Now there's going to be 2 factors affecting the ease of which a binary acid donates a proton, and that is the bond polarity and then the bond strength. So let's look at bond polarity. And these looks like pictures from first semester, and it most certainly is. So the bond polarity is going to help determine whether or not the compound is even acting as an acid. So hydrogen must be the positive element of the two elements in the binary compound. And what we see here, like in lithium hydride, the hydrogen is actually acting as the negative element in this compound. So therefore lithium hydride is not going to be an acid. Hydrofluoric, on the other hand, we see that the hydrogen is acting as the positive end, and it's most certainly, that proton from the hydrogen is most certainly attracted to that extremely electronegative fluorine. And so this is what's going to determine when you see a binary compound with this hydrogen plus an element, whether or not it's actually can be an acid. Is the hydrogen the positive element of the two elements in the compound? All right. The other thing that's going to determine whether or not the acid is strong or weak, the binary acid is strong or weak, is the bond strength. The stronger the bond, the weaker the acid. So notice that a lot of our strong acids are these halogens that are below fluorine. And we already talked at the beginning of this screencast about why hydrofluoric is a weak acid. It does not want to give up that hydrogen at all. It is the most electronegative element on the periodic table, and therefore it can hold on to that hydrogen and not let it go easily. So our acid strength actually increases as we go down our halogens. We also see that our acid strength increases as we go to the right on the periodic table. Now, CH4 being considered an acid, I would say that's a stretch. Even ammonia, is it really acting as an acid? No, it's really more like a weak base. So we really don't see true ability to act as an acid until we get over here to oxygen. But as we go down those halogens especially, we really see that increasing acid strength, as it is much easier for these halogens to let go of that proton that's attached to them. Once again, here's a great chance for you to stop the video and work problem 117. All right, let's look at these oxyacids. So oxyacids contain a hydrogen atom bonded to an oxygen atom. Then the oxygen atom is bonded to another atom. So here is our skeletal form, and here once again Y is representing some other element other than oxygen or hydrogen from the periodic table. So there are two factors affecting the ease in which a proton is donated: the electronegativity of that element Y, that other element that's not oxygen or hydrogen, and the number of oxygen atoms attached to element Y. All right, let's look at those two factors in a little bit more detail. So the more electronegative element Y is, the more acidic the oxyacid is. So here we see, here is all of our, let's say, element Y. And as the electronegativity increases of those elements, because remember, as we get closer to fluorine, we're going to become more electronegative. And for oxyacids, that means it's going to be a stronger acid. And then we also, the number of oxygen atoms attached to element Y. The greater the number of oxygen atoms bonded to Y, the stronger the acids. Now, why is that? Well, let's look at that. Remember, when we are trying to figure out the oxidation number, remember, oxygen is always going to be a -2. And then we're going to base the oxidation number of that other element around that 2. So the oxidation number, remember, the oxygen is a -2, the hydrogen is a +1, so therefore the chlorine for this one is also a +1. And so we're going to see as we move across here that the oxidation of the oxidation number of the chlorine is going to constantly change in order to keep this compound neutral. The only thing that doesn't change is the oxidation number of the oxygen and the hydrogen. And that's what's driving the changing oxidation number on these chlorines. And so what we see is that as that oxidation number increases, we end up with a very strong acid. Perchloric acid is one of those 6 strong acids that you need to memorize. Once again, go ahead and stop the video and work into chapter 17, problem 119. All right, ladies, that is the end of the lecture. That is also the end of our notes for chapter 17. And so I would look for us to have a quiz on this material next Friday, which I think is the 24th, but it would be next Friday. All right, ladies, y'all have a great day.